All right, so what we're going to be doing in the next few videos is constructing molecular orbital diagrams for molecules that have more than two atoms. So the diatomics were pretty easy. We had atomic orbitals, we mixed them, and could kind of go from there. Here, we're talking about AXN molecules. So these where A is a central atom and X are pendant atoms, just means ligands or atoms around the center, non-central atoms, okay? So it could be something linear, it could be something as complicated as octahedral. We'll get to that later on in the course. But we're gonna come up with a general strategy of how to tackle the molecular orbital diagrams for AXN molecules. And the problem is really, let's say you have three atoms, how do you add those? Do you add 1, 1, 1? How do you do constructive, deconstructive? Do you add 1 with 2? You can imagine that the 2 outside with the 1 inside. There's a lot of different combinations, right? And so there are indeed a lot of combinations. And what we need to do is devise a protocol that allows us to determine the symmetry of those different combinations, and only the ones with the appropriate symmetries, right, of the same symmetries can we add together. Because we know that only when we have the same symmetries are we not going to be orthogonal, and so the overlap integral is not going to be 0 in those cases. And so we're going to be looking for combining combinations that give rise to the same symmetry. All right, so we're going to add linear combinations of atomic orbitals of X, the ligands, that are compatible with the symmetry of the molecule. There's a name for what we're doing. We're going to be making what are called SALCs, or symmetry-adapted linear combinations. We're going to be taking combinations of the atomic orbitals on the terminal atoms, looking at the different combinations, seeing what combinations there are, and then we're going to be mixing them together according to their symmetry. So that's what this says. We're going to form molecular orbitals by mixing atomic orbitals of central atoms and the symmetry-adapted linear combinations, the SALCs, of similar energy and same symmetry. Okay, so we're going to start with an example. It's always easiest to see these things when looking at examples, right? And so the example is going to be a relatively similar one. This is known to be a linear molecule. This is beryllium hydride. Okay, so first things first, you got to identify the point group. So I'm just telling you that this is linear. You can use VSEPR to predict that this is linear, but we're kind of divorcing ourselves from VSEPR. So the point group here is going to be d infinity h. Why is it d infinity h? Well, there's a c infinity because this is linear. That's going to be the primary rotation axis going through all the atoms. And then there's a perpendicular C2, right? If you spin this molecule 180 degrees, H is going to go to H and vice versa. So it's d infinity H. So we can use that d infinity H point group throughout this process. Next, we need to make SALCs of the pendant atoms. Pendant atoms, again, just means ligands or non-central atoms. So those are going to be hydrogen. And, we have to think about what atomic orbitals we care about for bonding. Now, we're talking about ligands that are hydrogen. Hydrogen just has one s orbital. That's the only atomic orbital that's in the valence regime, right? There's no 2s there, 2p. So all we care about is the 1s orbital. So we only care about the s orbitals of hydrogen. Now, s orbitals can only make sigma bonds. In order to make a pi bond, you have to have two lobes, two sets of lobes interacting, right? We went over that definition of a pi bond. A delta bond, you need 4 sets of lobes. Phi bond, you need 6 sets of lobes. S orbitals have only one lobe, so the only sort of bond they can make is a sigma bond. And, a sigma bond is very directional. So it's only going to have bonding density, so to speak, towards these hydrogen atoms. So it turns out you can just, because of this, you can just represent a sigma bond as a vector. And so we can just represent it like this. Hydrogen is going to be bonding towards beryllium. We're setting up that bonding up. We're trying to figure out the symmetry of these interactions. So, you know, each hydrogen is going to kind of be pointing towards the central atom. And in order to come up with the symmetry adapted linear combinations, the salts for these 1s orbitals of hydrogen, all we have to do is figure out the reducible representation for these vectors, these pictorial representations of the sigma bonding. Okay? And so in order to do that, we are operating in the d infinity h point group. And so we're just going to ask, you know, how do these different vectors transform in d infinity h? So we have v1 and v2. So identity, obviously v1 is going to go to v2. And now what we've set up is sort of this v1, v2 space. And so v1 went to v1, v2 went to v2. This is going to give us a character of 2. And so just to be really clear about where this comes from, basically what we're doing here is we are thinking about this sort of matrix. We're asking the question, you know, how does V1 and V2 transform? Well, for identity, V1 and V2 just give back V1 and V2. So we have the identity matrix, 1s across the diagonal, 0 across the non-diagonal. So the character is just the trace, right, which is the sum across the main diagonal is 1 plus 1, giving us an answer of 2, okay? Same idea for C infinity. C infinity, remember, is going through here. And so it's a rotation there of any arbitrary angle. And you know, in doing that, we haven't changed the positions of V1 and V2. So we have that same identity matrix. So we have a value of 2. Same idea with sigma V. Sigma V is in the plane of the molecule here. And so doing a mirror plane there doesn't do anything to V1 or V2. Now inversion is a little bit different, right? What's inversion going to do? That takes left to right and right to left. And so, you know, you ended up with a point here. I was on the left. That's the beginning of the arrow. That went to the right, okay? And then you have the arrow head, and now that got flipped to the right. And so V1 went into V2. And so your matrix looks like this, right? Where V1 went into V2 and V2 went into V1. So you said, how does V1 and V2 transform? Well, it transforms into V2 and V1. Writing that not in a matrix form is shown right here. V1 going to V2, V2 going to V1. And that gives you along the diagonal zeros. So that's why we wrote a 0 right there. S infinity, that is very similar. It's also going to give you a 0. V1 goes into V2, V2 goes into V1. Why is that? You did C infinity. C infinity did nothing, but then you follow it by a sigma H, and that put V1 into V2 and V2 into V1. And then lastly, a C2. C2 is perpendicular. There's infinity number of them, but doesn't matter. You take 1. And again, that's going to take V2 into V1 and V1 into V2. That gives you a value of 0. It gives you this sort of matrix where you have zeros all along the diagonal. Okay? So now you have this reducible representation, and you need to reduce it. And so you have this value of 222,000, and you need to decompose that. And a little bit of a side here in a second, but the easiest way to decompose this is to just do this by inspection. So you can see pretty easily that sigma G plus sigma U plus is going to give 222,000. So here's sigma G plus, is 1s across the board, and here's sigma U plus, 1, 1, 1. Adding 1s to those will give 2s. Adding 1s to these negative 1s is going to give the 3 zeros here. Now, if this was a much more complicated problem, what would you have to do? You would have to apply the reducing representation formula that we learned way back in chapter 2. And so if you did that, oh, and by the way, just, these are the two salcs, what they look like. And I'll show you later how you can come up with these pictures. For now, I think you can see this top one, that's sort of like a symmetric interaction. They're not actually bonding. We haven't done any bonding yet. We're just setting up the salcs. Remember, these are the 1s orbitals that we're talking about. So the hydrogens don't bond with one another. They're way far apart, right? And so the beryllium atom is in the middle here, right? In both of these. But I mean, I think you can guess, and you could test the symmetry of this, that when they're both the same shade here, that's going to be the sigma G plus orbital. And then when they're opposite shades here, they're going to be the sigma U plus orbital. And again, how would you show that? You could do inversion on this, right? If you did the inversion operator on this, well, dark would go into the light portion here and light would go in the dark portion here. So that would get you a value of -1, just like this sigma U plus representation is. And you can confirm that with all of these different operations that, you would get 1, 1, 1, -1, -1, -1. So anyway, that is where we're going to leave off here. One thing I was going to point out, and I'll get to you later, later on in the course, I will show you that if you apply the formula, so we just reduced this by inspection, right? We just kind of looked, and there's kind of a puzzle to figure out, oh, okay, yeah, sigma G plus sigma U plus gives me that gamma salc representation. If you were to try to apply the formula to this, you actually can't. And the reason why you can't is because that formula back in chapter 2, it has a 1 over the order. And the order of the point group here is infinity. There's infinity symmetry operations. You have infinity C2s that are perpendicular and infinity sigma Vs. So right now it wasn't a problem because we didn't have to, we could just kind of look at this and come up with the answer. But later on in this chapter, I'll show you, a workaround for how you can still use that formula. But we have to introduce some other concepts first. So, but that's not the main point here. The main point here is that we are able to represent sigma bonding as vectors. And again, these were s orbitals, right? We represented them as vectors, and we're setting up doing bonding. We haven't done any bonding yet, but we're looking at the different combinations of these 1s orbitals, and we found 2 combinations, okay? And these 2 combinations have 2 different symmetries. And so we can write that gamma salx is equal to sigma G plus, one of them, and the other one is sigma U plus.